You know when you look at a university exam, what do you see? Just a bunch of questions, right? Well, what if I told you it's not a test at all? What if it's actually a set of encrypted messages? Messages that hold the secrets to one of the most powerful languages in all of science and technology. Today, we're going to decrypt one. Let's dive in and crack the linear algebra code.
It really all boils down to one fundamental question. How do you use math to describe something like a space? And maybe more importantly, how do you describe all the ways it can be stretched, squashed, twisted, or changed? That's the heart of everything we're about to explore.
So, our first puzzle has two main parts. First, we've got to get a handle on the space we're playing in. Think of it like the game board, you know? It has its own rules, its own dimensions. And second, we have the instructions. These things called transformations that tell us exactly how to change that game board.
Whoa. Okay, so here's our first piece of code. Now, at first glance, this looks like a total mess, right? It's defining a space of polynomials, but it just seems like a jumble of letters and pluses and minuses. How on earth are you supposed to make sense of this? This is our space, U.
But here's the secret to cracking a code like this. You have to look for the most basic parts. We can actually untangle that whole formula just by grouping all the A's together, then all the B's, and finally all the C's. We're basically factoring out the variables to find the real building blocks underneath. And boom, look at this. It turns out that entire complicated-looking space can be built from just these three simple polynomials. That's it. Any element in that whole universe can be made by just mixing these three together. We found its basis, its Lego bricks. So now that we know our world, what happens when we try to change it?
Okay, with our space all mapped out, the next piece of the puzzle is to apply one of those instructions, a transformation, and just see what happens. And this is where it gets really interesting, because some instructions, well, they break things.
Now, this slide is super important because it shows you how abstract theory becomes a real practical tool. On the left, we've got this condition from the exam. It basically says we're looking for a situation where doing two transformations loses more information than just doing one. But here's the cool part. That abstract idea points us directly to an amazing tool on the right, the determinant. You can think of the determinant as a single magic number that tells you if a transformation squashes space flat. If it's 0, a dimension gets lost. That's our clue.
So we do the math, we calculate that determinant, and we figure out when it equals 0. And the calculation tells us this particular transformation only breaks at two very specific points, when this little parameter a is either 0 or 1. These are our weak spots.
But remember our original condition. We have to check both of these values. So if a is 0, the rank, which is just the number of dimensions left over, is 2 in both cases. No difference. So that's a no. But look at a equals 1. The combined transformation has a rank of 2, while the single one has a rank of 3. That's a perfect match. So a equals 1 is our answer. Puzzle 1, solved.
All right, let's level up. For our second puzzle, we're going deeper. We're not just looking at what the transformations do to a space anymore. Now we're trying to understand the internal structure of the matrix itself. We're going to find its hidden skeleton.
And this hidden skeleton? It's made of things called eigenvectors and eigenvalues. Now, they sound intimidating, but the idea is actually beautiful. Eigenvectors are the special directions in space that don't get knocked off their axis by a transformation. They just get stretched or shrunk. And the amount they get stretched by? That's the eigenvalue. They're the true, unchanging core of the transformation. So how in the world do we find these things? Well, it takes another piece of code, the characteristic polynomial. Think of this as the key that unlocks the skeleton. By figuring out where this polynomial equals 0, we can find the eigenvalues, the exact stretching factors. And here they are. The solutions, or roots, of that polynomial give us our eigenvalues, a, 2, and 6. These are the fundamental bones of our transformation's skeleton. And if they're all different from each other, we have a nice, complete skeleton.
And that leads to the crucial question. What happens if a isn't some new number? What if a is actually equal to 2 or 6? Now we've got repeating eigenvalues. It's like having a blueprint for a skeleton that has duplicate bones. It might not fit together right. It might be defective. So let's test it out. Let's look at the case where a is 6. We run the numbers to find the eigenvalues and, whoa, look at that. Do you see it? A whole row of zeros at the bottom. That's a massive visual clue that something's gone wrong. A dimension has literally collapsed. We've lost a piece of our skeleton.
And here's the mathematical reason for what we just saw.
For that eigenvalue of 6, the algebraic multiplicity, you can think of that as how many times the blueprint said we should have that bone, is 2. But the geometric multiplicity, the number of actual independent bones we could find, is only 1. The blueprint doesn't match the reality. The skeleton is incomplete. And the mathematical term for that is non-diagonalizable.
As it turns out, the exact same thing happens if A is equal to 2. So the final answer to puzzle number 2 is that this transformation has a defective skeleton. It's not diagonalizable. When A is 6 or 2, we found the bugs in the code.
Okay, so we've solved these abstract puzzles, but why does any of this actually matter? Well, because this code isn't just for exams. This is the language that literally builds our modern world.
Seriously? Every time you see a character run in a video game or a 3D model get rotated on a screen, that's linear algebra in action. Matrices are the instructions that are scaling, rotating, and moving all those objects around in virtual space.
And how about search engines? The core idea behind Google's original PageRank algorithm was pure eigenvectors. They imagined a massive matrix representing the entire internet and found its principal eigenvector, its main skeleton, to figure out the importance of every single web page.
And today, if you look at machine learning and AI, well, linear algebra is everything. It's the bedrock. It's used to analyze huge data sets, shrink down complex problems, and build the neural networks that are changing our world. It's the grammar of data. Which really brings us to a final thought. We've just seen how these really abstract ideas can describe the hidden skeleton of a mathematical transformation. It just makes you wonder, what other invisible structures are all around us, in nature, in society, just waiting for us to find the right mathematical language to finally see them?